So good afternoon, everybody. My name is Prajval. I'm a PhD candidate at the BMW Group and the University of Glasgow. And I'm excited on behalf of my co-authors, I'm excited to present our research titled An Empirical Evaluation of Various Information Gain Criteria for Active Tactile Action Selection for Object Pose Estimation. So you may be familiar with this scenario wherein we as humans, when it's dark and we want to search for objects which we want next to us, we rely on our hands, we rely on the sense of touch, and we do it very efficiently. With about 3 or 4 touches of the object that we want to, we are able to identify where the object is. We are able to identify the pose, the position, and the orientation of the object. We want to give robotics a similar capability. We want to give robotics equipped with tactile sensing to be able to identify robustly and accurately and efficiently the pose of objects just using tactile sensing. There are challenges for this. The first is that robots equipped with tactile sensors essentially give very sparse data. They give very sparse point cloud data upon contacting these objects. These point clouds are extracted from the 3D positions of the contact points when the robot touches the object. So we need to develop an algorithm which can identify the position or the pose of the object from sequentially acquired sparse data. Connected to this issue is how to acquire data. One way to do is a naive approach would be to have a grid search, or like to uniformly acquire the data along the boundary of the object and completely cover the object by touching it. But this is very time consuming. Hence, we need to do it strategically. We need to have a strategy on how to acquire data in an active formulation like humans do it. To address these challenges for the first time, we propose a novel method, which is based on point cloud registration. The method is termed as translation-invariant Quaternion filter. In this, we take a source point cloud, which is of the object that we want to find out, and the target point cloud, which is coming from the tactile sensing, from the robot which is equipped with the tactile sensor. And first, we extract what is called translation-invariant measurements, wherein the raw point clouds we decouple the rotation and translation by taking the vectors between the raw points, and then we can estimate rotation using a Kalman filter. In this case, we have a classical Bayesian filtering framework wherein we have a prior pose belief, which is sequentially updated using the measurements that we get from the tactile sensing to iteratively update our pose belief. Once the Kalman filter converges, we can estimate the translation in closed form. What is the advantage of our proposed method is that it works very well for dense as well as sparse point cloud data. And due to the formulation, it implicitly allows active action selection. So what is active action selection? The aim of active action selection is to allow the robot to autonomously choose the next best action by reducing the uncertainty and by maximizing the information gain. This allows the robot to identify the pose of the object with very minimal actions. So how we do it is that given our current pose estimate from our TIQF formulation, we can sample multiple different actions and then choose the one which gives us the most information gain. As you see here from the Gaussian distributions, we choose the one which the next best touch is chosen from the information gain criteria. To formulate this criteria, we take information theoretic concepts called such as Kullback-Leigh blur divergence, the Renyi divergence, the Fisher information metric, the Bhattacharya distance, and the Wasserstein distance. We validated our proposed method both in simulation and in real robot experiments. In simulation, we took the Stanford scanning repository. Here you see in the red point cloud, you see the target, and in the green point cloud, you see the source. The black points show the actual measurements, the very sparse measurements, and you see that iteratively by taking actions which are taken in an active formulation, we're able to find the pose in a very robustly and in very minimal amount of data. We also validated this on a real robot. Here you see a robot equipped with tactile sensors trying to identify where this bottle is in the world, and it is choosing where to touch the object using this information gain criteria, so that it can try to identify its position and orientation in a very robust and in a very efficient manner. And you see that within about 4 or 5 touches, it's already very highly accurate, as you see in the top right corner. On average, we tested this across different simulation experiments and real robot experiments for different objects. And we see that within about 15 number of actions, tactile actions, we're able to get an average accuracy of less than 1 centimeter error. And we also tested with different information gain criteria. And we see that the conversion rate is almost similar for all the different criteria. And it all converges to about less than 1 centimeter average error accuracy. In conclusion, we've proposed a methodology wherein we can achieve autonomous tactile-based pose estimation for robotic platforms with very high accuracy of less than 1 centimeter error with very minimal number of actions, which are chosen actively. We provide a framework wherein we can apply the concepts from information theory to robotic tactile-based pose estimation. We can also correct ambiguous visual pose estimates with tactile data, and we have also investigating that this TIQF algorithm can be easily extended to other applications, such as in the autonomous vehicles domain for LiDAR data, which is also dense and sparse. We can also investigate how to do this for example, for mapping, for active SLAM, and so on at BMW. So thank you very much. I'm very happy to answer any questions that you may have.